Hello, everyone. So today we're going to be talking about Helmholtz free energy. So this is essentially just going to be another way that we can talk about the spontaneity of a reaction. And so it's worth noting that whenever we're really talking about the spontaneity of a reaction, or whether a reaction is going to can occur naturally, or whether I have to put in energy to drive it, we should always return to the idea of the entropy of the universe, because this is really the property that dictates whether a reaction is favorable or not. And so we often, again, so for a reaction to be favorable, our entropy of the universe has to be increasing. So at the very least, we're going to have a reversible system where the entropy of the universe is equal to zero. But ideally, in order to make sure the reaction occurs favorably, we're going to want the entropy of the universe to increase, which means we're either going to have to see some increase of possible states in the system or in the surroundings. So again, the entropy of the system is often going to be dictated by what actual change is happening, whether it is a pressure change, a temperature change, or a chemical change. This means that a lot of the variability in what's happening is occurring under the surroundings level. So how much heat is being put into the surroundings, as well as what is the temperature of my surroundings. The more heat being put into the surroundings, the more I'm disordering the surroundings. But this is going to have a greater influence at lower temperatures. And this is going to be one of the larger driving things of whether a reaction is favorable. However, we often really hate talking about the surroundings, so we've previously replaced this with the heat of the system by essentially just flipping the sign. Now, again, more heat released from the system, more favorable the reaction, uh, uh, the lower the relevant temp, the more this has an influence, and the less influence the entropy of the system has. However, we run into some slight issues because heat of the system is a bit of a path function, making entropy of the universe also a little bit path dependent. So what we need to do is try and constrain our system to replace heat with a state function. Thankfully, we have plenty of practice with this. So in order to constrain our system, one of the classic choices is to go to an isochoric system. This is the classic choice of a lot of chemical engineering and mechanical engineering, because you're often just looking at solid state systems that don't actually change in volume. Well, under this case, the entropy of the universe is going to be equivalent to the change in entropy of the system minus the change in internal energy, because again, this is going to be equal to the heat under isochoric conditions, and then our temperature stays relatively untouched. So what this ends up turning into is that the favorability of a system is going to be related to the change in entropy and the change in internal energy. However, it is worth noting that most of the time, we're going to be dropping the subscripts when we're talking about the system. So if you do not see a subscript, just go ahead and think about system. Now, this does pose some problems that you need to be very deliberate when you're talking about total entropy or surrounding entropy to help distinguish it from the system. So now if I've got an isochoric system, I can determine whether or not a reaction is favorable simply based on the change in internal energy and entropy, which we now know how to calculate from literature values. However, let's be honest, entropy of the universe is a little bit of an odd notation to work with. So we're going to essentially try and clean up our notation by multiplying both sides by negative t, which turns our internal energy, isolates our internal energy term by itself, and then minus the temperature times the entropy of the system. So all of this is going to be equal to negative T times the universal entropy, change in universal entropy, which we essentially shorthand as the change in the Helmholtz free energy. So Helmholtz free energy is going to be another metric of the favorability of a reaction. So just like universal entropy, is going to indicate a favorable reaction if our universal entropy is positive. Similarly, because of the negative sign, a reaction is considered favorable if the Helmholtz change in Helmholtz free energy is less than or equal to 0. So again, we have a bit of a sign change. However, it does turn out that our Helmholtz energy actually does have some additional physical meaning besides just an indication of favorability. And we can actually derive this by kind of going back to our old friend, the first law, because we know that the change in internal energy is going to be the same as the work plus the heat of entering the system. However, because these are two path functions, and this is a state function, I can artificially constrain my path function. So I know the sum of these two is also going to be the sum of the minimum amount of work and heat required, of the reversible heat and work and heat required, which if I'm talking about the work being accomplished by a system is going to be the same as the maximum amount of work that I can get out of the system and the minimum amount of heat needed to drive it. So using this essential notation, what I can then do is put this expression into my Helmholtz free energy equation. So I now know my Helmholtz free energy equation is going to be equal to the maximum amount of work the system can accomplish plus the minimum amount of heat needed to drive it minus T delta S. Well, it turns out we have already defined our reversible heat as T delta S from our definition of entropy. So we can then go ahead and plug in that expression, and what we end up having is our Helmholtz free energy is equal to the maximum amount of work the system can accomplish plus T delta S minus T delta S. So it turns out the change in Helmholtz free energy is again going to be a shorthand notation for the maximum amount of work I can accomplish, a system can accomplish. So if I say have a chemical reaction, say a combustion reaction, we can actually determine the maximum amount of work that combustion reaction can accomplish simply through the use of the Helmholtz free energy. And let's be honest, from an engineering perspective, that makes Helmholtz an incredibly powerful sort of expression. So if I have a reaction, I can determine how much work I can extract from the system. But let's say if I have a chemical reaction that is unfavorable, so I have a negative Helmholtz or positive Helmholtz free energy, then this tells me the minimum amount of work needed to drive that reaction forward. So again, from a very practical perspective, this is a useful sort of metric to tell about how to drive a system forward. And so it is worth noting that we can also, again, break this into kind of components. So the change in internal energy is going to be telling me a lot about the change in energy of the system. So how much energy is the system, say, producing or consuming if it's positive? Similarly, the T delta S is going to be telling us a lot about how much energy is going into or coming from random motion. So let's say I have a positive delta S. Well, this means I have a positive entropy. So the entropy of my system is increasing, but this gives me a negative value, which ends up showing me I have a negative, leading towards a negative Helmholtz free energy. So this means I essentially am losing, I am increasing the amount of random energy in random motion of the system, which again is driving this favorability of the system. Now, we can also turn this into, say, more of a practical consideration of looking at a real kind of reaction. So let's go ahead and try and determine the Helmholtz free energy of the vaporization of water. So I go from liquid water to gaseous. So I can go ahead and look up the standard state literature values. So the standard state change in internal energy is about a little less than 44 kilojoules per mole. And we also see an increase in entropy, or a positive value of 118 joules per mole Kelvin. So again, this system is consuming energy, but it's producing energy in the form of random motion. Now, at this standard state condition for which these values are tabulated, what we find is that the amount of energy being consumed by the reaction is going to actually be much more than the amount of energy being produced by random motion. So we end up with a positive Helmholtz free energy of 8.6 kilojoules per mole, which means that if I'm trying to drive this reaction forward, I'm going to need to put in 8.6 kilojoules per mole of energy in form of work or possibly heat in order to drive this reaction forward. Now, this can actually be quite important if, say, I'm trying to sweat. Because if I'm trying to sweat, well, then this energy is leaving me and going into the water in order to drive the reaction forward. And this is the reason why sweat has such a cooling influence, because you're taking energy from yourself and using it to drive a chemical reaction. Now, it is worth noting that we also are going to be concerned about this reaction under temperatures that aren't standard state. So let's go ahead and look at 100 degrees C. So what we can do is uh, use a series of approximations and say that, well, my entropy of vaporization over 75 degrees, or my entropy and internal energy of vaporization over 75 degrees isn't going to change too much. And this is actually not the worst approximation. So I can essentially leave these two values constant and essentially put in my new modified temperature for 100 degrees C. And when we do this, we find that the reaction is slightly favorable at about negative 0.2 kilojoules per mole. Now, based on what we know, we'd expect this reaction to be completely reversible at 0 kilojoules per mole. Now, you might assume that some of this difference is coming from approximations we made in our internal energy and entropy. In fact, it turns out that a lot more of this comes from the fact that we made a more severe approximation. This is for isochoric conditions. And indeed, it turns out that if you try and boil water under isochoric conditions, it will indeed boil faster because it can essentially boil at a slightly lower temperature because we're not expending energy in the form of work. Because again, we're working with a closed system. So Helmholtz free energy is a very useful metric, but it is again far more interested in isochoric conditions. Now, we're chemists, we tend to care about isobaric conditions. So we're going to need to generate a new state function to look at the favorability of reaction under isobaric conditions. So next up, Gibbs free energy. Till then, take care.